Second video survey. I want to start by saying there are other calculus videos on this channel that might be useful to you. They should be sorted by topic. We're talking about limits for now. So the videos on limits might be useful to you. Let's start by looking at help questions. I see 2 topics listed. I see people want help with function notation and evaluating functions. So let me write that here. Function notation and evaluation. And the second thing you said is derivatives. And here's the thing. Derivatives are going to be a huge part of this class. But we're not going to start talking about derivatives for another week and a half almost. So I think I'm just going to save this one for later. Okay. I'll talk about it in a future video. Right now, we just want to be focused on limits. That's what's going to be coming up on our test next week. So I do appreciate the enthusiasm of wanting to get into derivatives. It'll be really cool when we see what derivatives do. But we're just going to hold off a little. And I hope that doesn't disappoint. So we're going to talk about function notations and evaluations. So usually what people are talking about when they talk about function notation is this kind of expression. This is called a function definition. This letter here is called the name of the function. This is our input. And this expression defines the function. So what that means is anytime we see something like this, we know that we're using the function f, so we're going to use this definition. We're going to plug in a 1 everywhere we see an x in that definition. And then we simplify and do arithmetic as normal. 1 times 1 is 1. 1 times 2 is 2. 2 plus 3 is 5. We say that f of 1 equals 5. If I plug in a different number, the x changes to whatever that new number is. 2 squared is 4. 2 times 4 is 8. 8 plus 3 is 11. This means that f of 2 equals 11. Now, functions can be used in arithmetic. I'll still have my same function, f of x equals, I think I said 2x squared plus 3. Let's see. I'll use the same f, but now I'll define a g function. Now I can do things like f of x plus g of x. Maybe I can simplify that. 2x squared plus 3 plus x minus 3. 3's cancel. I get 2x squared plus x. I can plug values into a function. I get the same 5 that I had before. F of 1 is still 5. But g of 2 is going to be 2 minus 3. So 5 plus 2 minus 3 is 4. Say f of 1 plus g of 2 is 4. I can also plug functions into each other. Everywhere I see an x in the original function f, I'm going to replace that with the equation for g. So I have 2x squared, but instead of x, I'm going to write the equation for g, the definition of g. And I can simplify this using the algebra that we should know already. Two times 9 is 18. 18 plus 3 is 21. This is f of g of x. Sometimes also written as f of g of x. This circle is hollow when I'm doing compositions. It's solid when I am doing multiplications. So f dot g of x means the function f times the function g of x, which I think was 2x squared plus 3 times x minus 3. F with an open circle g of x is f with g plugged into it, which is what we did. Okay, so that is what I have to say about function evaluation and function notation. If you have more questions on this, go back to the help page. I'm going to make another video on Monday. So you can put your questions there. If I didn't quite answer the question you were looking for, please. I'd like to talk a bit more about, I think that last time we looked at section 2.3 in the textbook. So let's take a look at that. 2.3, we're evaluating some limits. Let's go. The main way we're going to evaluate limits in this class is by trying to factor cancel so that we get a continuous function. Last time we talked about continuous functions or functions whose values equal their limits. A picture of such a thing might look like this, where the value of this function is whatever the y-coordinate is there. Let's call this point x equals a. The value is f of a. It's the height of the graph. The limit is whatever height the graph is pointing to from both sides. And for continuous functions, those values are the same. For discontinuous functions, we might have something that looks like this. This might also be the point x a. So in this case, g of a is this value. But the limit as x goes to a of gx is this y value down here. Since they're not the same, we say the function is discontinuous. Now, there are a few types of continuities that we can talk, or about of discontinuities we can talk about. The type we have here is called removable because removable discontinuities are the ones where if you just moved one point up or down, you could fix the problem and get a continuous. Removable, you're allowed to move one point. You're only allowed to move it up or down. Grab one point and shift it up or down so that it fills in the gap and you get a continuous function. That's a removable function. You can also have what are called jump discontinuities. Or you can have asymptotic discontinuity. I always forget if asymptote has one or two S's. I think it's just one. So an asymptotic discontinuity. And then there's another one that you, you'll see sometimes mentioned. It's called an oscillating discontinuity. And the way that an oscillating discontinuity works is you have an infinite number of wiggles as the x value goes to some fixed x value. So an example of this would be like y equals sine of 1 over x. If you type that into Desmos, you get basically this graph here, but centered on the x-axis. So the reason that these functions are not continuous is because in these three cases the limit doesn't exist. There is no single y value that the function points to here. No limit means that the function can't equal the limit, means discontinuous, and irremovably so. Irremovably discontinuous. All of these are irremovable discontinuities. Again, there's no single y value that's being pointed at by this function, so there's no limit. And again, like as I'm doing an oscillating discontinuity, you can't tell, does it point to that y value or this one or this one? So again, no limit, so no, it's a discontinuous function. No limit, discontinuous function. These three are irremovable discontinuities because I can't fix them and make them continuous by moving a single point. Removable discontinuities, again, you just grab one point from wherever it is and move it up or down, fill in the hole. Okay. I think I already looked at the 2.3 homework questions, so I'm going to go look at the 2.4 homework questions now. One to 134. Okay. says for the following exercises, determine the points at which each function is discontinuous. I'm going to look at. I'm going to do 133. I think you should be able to figure out how to do the rest of them on your own. Although, if you get stuck, please let me know and I'll see if I can answer your question on Monday. We have a function. And I want to figure out if there are any discontinuities of this function. Well, I notice if I factor it, I get this. And then I can cancel that, get this. Now this function here has an asymptote at x equals 1. So it's going to have an asymptotic discontinuity there. But since I was able to cancel out a linear factor, it also has a removable discontinuity. Movable. At x equals 0, because I can't divide. If I plug in 0 to the original function, exactly what I do. This function, there are a few steps to graphing it. I'm going to say, I'm going to graph by parent function here. My parent function, g of x equals 1 over x. This is, g is shifted 1 to the right. So instead of having g's asymptote that looks like this, I'm going to shift 1 to the right. Here's my asymptote at x. And that's the only change made to this. Well, that's not entirely, because we also have the discontinuity. But here is my shifted function. And then at x equals 0, which is here, I need to put a nice little open circle to represent the removable discontinuity. I'll label that as 0, -1. And I do that because if I plug -1 into my function, I get, or if I plug 0 into my function, I get 1 over -1, which is negative. So I've marked my asymptote. I've marked my movable discontinuity. I've done the shift that puts my function in the correct place. This is a graph of f of x. Did it ask to graph? It said for the following exercises, determine the points, if any, at which each function is discontinuous. Classify any discontinuity as a jump, removable, infinite, or other. Infinite is just another way of saying asymptotic discontinuity. This book uses the term infinite discontinuity. That's fine. So we already did that when we found the removable discontinuity at 0 and the asymptotic discontinuity or infinite discontinuity at 1. So this graph was fun to do, but it wasn't part of the question. You can check these by plugging them into Desmos. Desmos will find all of your jump discontinuities and your asymptotic discontinuities and your oscillating discontinuities. It will not find removable discontinuity. Removable discontinuities are so small that Desmos, which is a great tool, Desmos is a great tool, but Desmos typically doesn't find. removable discontinuities well, or they don't show up on the graph well. Look at 159. For the following exercises, get your graph with the property. We want discontinuous at x equals 1. Discontinuous at x 1. We want the limit as x goes to -1 of x to equal -1. And we want the limit as x goes to 2 of f of x. So at -1, I want it to approach -1. So I'm going to put, doesn't say it has to be f y equals f of x. Yeah. It doesn't say that the function has to be discontinuous at -1. It doesn't say that it has to be continuous. I'm just going to put a dot right here and a little line coming off of it. That'll get me the limit that I want. And then at 2, we want the limit to be 4. It doesn't say it has to be continuous. It doesn't say it has to be discontinuous. I chose the last one to be continuous, so I'll choose this one to be discontinuous. I'll just do that. Now the limit is 4, even though the value of function is not at x equals. Then it says discontinuous at x equals 1. So I'll do a jump discount. There's my function. Discontinuous at -1. There's my jump discontinuity. The limit from the left and right is -1 at x equals -1. And as x goes to 2, that limit is 4 from the right and from the left. So there we go. This is a perfectly acceptable answer to that question. (161, 66). Justify whether each of the given statements is true. Justify your response with an explanation or a counterexample. F of t equals 2 over... This one might be a little hard. F of t equals 2 over the t minus e to the negative t. Okay. So I'm going to give you a tool that's really nice. It's a nice theorem, which says that elementary functions are continuous on their domains. That is a theorem that I'm giving you. You can use it like. I'll give you another theorem, and that is some difference product quotient and composition of continuous functions is continuous where defined. Okay, so those two tools will do a lot of heavy lifting. So exponential functions are elementary functions. That means that this is continuous. This one is 2. The difference of them is continuous. And constants are elementary functions, so they are continuous. So we have a continuous function divided by a continuous function, which is continuous, except possibly where the denominator equals. So we have the question, is that denominator equal to 0? Or I guess I should say, does e to the t minus e to the negative t equals 0? If it does, that means e to the t equals e to the negative t. We can use the natural logarithm, get t equals negative t. The only number where negative t is t equals 0. So t equals 0 is the bad point. So the answer to this question is no. F of t is discontinuous at t equals 0. Number 64 asks about the intermediate value theorem. So let's talk about the intermediate value theorem. Intermediate value theorem says if f is continuous and L is between f of A and f of B, then there exists C between A and B such that f of C equals L. That might sound confusing. Let's draw a picture. So let's suppose this value is x equals A and this value is x equals B. Let's suppose this value is f of A and this value is f of B. So if f is continuous, that means the limit equals the function at every point, and L is between f of A and f of B. So let's pick an L. This is the line y equals L, between f of A and f of B. Then there exists C between A and B such that f of C equals L. So no matter how our function travels, if it's continuous, there is some point where f evaluated at C, which is the x-coordinate of this point, is equal to L. Or in other words, the function has to cross the line y equals L. If it's above the line somewhere and below the line somewhere else, it had to cross the line to get down. Now, if our function's not continuous, like for instance f of x equals 1 over x, is not continuous, then maybe we let L equal 0, and we see the function never crosses the line y. But that's because there's a discontinuity. We have an asymptotic discontinuity at x equals 0. That is how the function is able to get from above the line to below the line without crossing it. So let's look at question 164. It says, according to the intermediate value theorem, cosine x minus sine x minus x equals 2 has a solution. Cosine x minus sine x minus x equals 2. We want to prove this has a solution. Between negative 1 and 1. So let's try this. First off, I'm going to define a function f of x equals cosine of x minus sine x minus x. This is continuous because polynomials are continuous. Polynomials are elementary, so they're continuous. Trig functions are elementary, therefore they're continuous. And adding, subtracting, multiplying, dividing, and composing elementary functions gives a continuous function so long as it's defined. There's our function. If I plug in f of negative 1, I get cosine of negative 1 minus sine of negative 1 minus minus negative 1 is plus 1. Okay. Hmm. So mm, so we need to pull out some facts about cosine and sine. And some facts about radians. So pi is a little more than 3, but it's less than 4. Pi over 4 is going to be, this is less than 1. Or let's look at this one. This one is less than 1, which means this one is more than negative 1. And since pi is a little more than 3, this is going to be bigger than 1, and this one is going to be less than negative. That means that 1 radian is somewhere in here, and negative 1 radian is somewhere in here. This is going to be helpful, I hope. So, what this tells us is that cosine of negative 1 is going to be I'm probably overthinking this. They're probably expecting you to just plug this into a calculator. This question. we don't necessarily have to do that part by hand. Let's plug in cosine of -1. We want to make sure that this is set to radians first. We're working in radians. -1 to cosine of that. Okay. So we get 0.540, all of that. Let's we store that to memory. And then I want to do sine of -1 as well. Okay. So sine of -1 will be, didn't quite type it in correctly, did I? Okay, sine of +1, sine is an odd function, so sine of -1 is just the negative of this. I have cosine, which is 0.54. I have sine minus sine is going to be minus negative that, so that's going to be plus 48. Let's try doing this again. So we have -1 and we plug it into cosine. We get this value. We take -1 and we plug it into sine and we get this value. We're going to subtract that off, so that's going to flip signs. We add this. $1.68 seems a little big. But I think that's what the calculator said. I'm not going to second guess that. So we have f of -1 equals 1.68. We're going to add 1 to that and get 2.68, which is definitely above 2. Now I'm going to try f of 1, which is going to give me cosine of 1. And we're going to subtract sine of 1 and add 1 to it. So start off with our cosine value, which was this one. Okay. I plug in a 1. I plug in cosine. I get that. And then there we go. We have our number, and we're going to subtract sine of 1. Sine of 1 is first we type in 1, then we type in sine. There's sine of 1. We're going to add this to our cosine value, which is this one. I know why it says 1.86. It's because it's adding sine to itself and not adding sine to. Got it. 1 sine gives me that. I want to add it to 0.5403. That should be enough digits. We get this. and then we're going to subtract 1. And we get 0.38. So this is equal to 0.38, which is less than 2. This one up here, we need to redo because calculator didn't work as I expected it to. So with that one, we go -1, plug that into cosine, and we get this 0.5403. Remember that. Type in -1, we type in sine, get that. We're going to subtract that, so we flip the sign on that. Did it not take the negative that time? -1 sine. We're subtracting it, so we flip the sign. We're going to add that 0.5403 to it, because that's the cosine. Then we're going to add 1 to it. This gives us 2.38, which is still greater than 2. I think we got a little lost in the weeds there. But the point is that we are using our intermediate value theorem to show there's a solution to this equation. The way that we're going to do that is to define this as a function and show that here's the line y equals 2. If the function is above it somewhere and below it somewhere, had to cross it somewhere, and that's where the solution is. So we plugged in the -1, we got a value that's bigger than 2. We plugged in the +1, we got a value that is less than 2. That means that by the intermediate value theorem, there is a point between x is 1 and x is -1. Give it a name. That point has to satisfy the equation, which is the same as saying that cosine of c minus sine of c minus c equals 2. The equation that we were trying to solve, there is a c value that solves it. And it's somewhere between -1 and -2. I think I'll let you do the rest of these in the 160s. And if you get stuck on one, send me a message. I'll answer it on Monday. I think that that's. Well, we should also preview work 3. Take a look. So, work 3 is when we start derivatives. That's good. We'll do some limit definition of derivatives, 3.1, the problems, 7. Yeah, so that's definition of the derivative stuff. There are videos on the definition of derivative on this channel. Um, I'll do 1 or 2 of these on Monday. They're not going to show up on the test. The derivatives come after test. So I'll show you an example of one on Monday. Don't worry about it for the test, but I want to show it to you so that you can think about it when you're doing the homework that's due after the test. And then 1.3 is it's going to be more derivatives. It's some differentiation rules. So that's where we'll learn the product rule, the power rule, the quotient rule. And again, that's not going to be on the test. That's next week. So I don't want to confuse you. I'll do a couple problems on Monday, and I'll make sure that I stress that it's not going to be it's going to be um okay. Now, one thing is I was checking exam 1 today, and I found that some of the graphs disappeared. So I will get that fixed. The test should be available on Monday. I think that just to make sure that nothing goes bad, I'm going to publish this exam so that students don't accidentally. But it'll be operational on Monday. Have until Friday to maybe Saturday to take. It's due on September, whatever day of the week. I'm gonna take that offline. It's the papers on it. So that should be everything for today. I'll see you again on Monday. I'll answer whatever questions I get between or now and then. So have a great weekend. Good luck on the homework and good luck on your studying.